Hello, and welcome back to Sleep Science Time. I'm so glad you've chosen to join me here tonight. Find a place where you can feel completely at ease, letting your body settle into comfort. Allow the noise of the day to gently fade, like a distant echo, and bring your awareness to the simple, steady rhythm of your own breath. There is nothing you need to do, and nothing you need to know. This is a space for quiet curiosity, a place to let your mind wander through some of the most profound ideas in science as you drift peacefully towards sleep. Tonight, we're going to open a door to a hidden world. It is a world that exists all around us, and even within us, yet it operates by a set of rules so contrary to our everyday experience that it can feel like a dream. This is the world of quantum physics. Before we step through that door, let's take a moment to appreciate the world we think we know. It is a world of comforting certainty. If you drop an apple, it falls to the ground. The sun rises in the east, and the planets move in predictable, graceful orbits. For centuries, this was the universe as we understood it, governed by clear, sensible laws laid out by thinkers like Isaac Newton. It was a classical world, where everything had a definite place and a definite path. By the end of the 19th century, many scientists felt that the great work of physics was nearly complete. It seemed as though we had a complete instruction manual for the universe, but as our tools became more precise, we began to notice a few small, persistent puzzles, tiny cracks in that perfect classical foundation. One of the first puzzles came from something as simple as a hot, glowing object, like a piece of metal in a blacksmith's forge. According to the classical laws of physics, the equations predicted that such an object should release an infinite amount of energy in the form of ultraviolet light. This was a nonsensical result, famously called the ultraviolet catastrophe. The universe should have been flooded with dangerous radiation, but it wasn't. The predictions were wrong, and no one knew why. The answer came in the year 1900 from a German physicist named Max Planck. He proposed a radical, almost reluctant idea. What if energy wasn't a continuous flowing stream like water from a tap? What if, on a very small scale, energy was grainy? What if it could only be released in tiny individual packets? He called these packets of energy quanta. This was the first whisper of a new reality. The idea that the smooth, continuous world we see is an illusion, and that underneath, the universe is built from discrete, indivisible steps. This single, strange idea was the key that unlocked the door. It was the birth of quantum physics. And in the chapters to come, we will gently step through that door together to explore the beautiful, mysterious, and deeply peaceful world that this idea revealed. A world of uncertainty, of particles that can be in two places at once, and of connections that defy space and time. Now that our journey has begun, let your mind settle into a state of gentle curiosity. The door to the quantum world is open, thanks to Max Planck's strange idea that energy comes in tiny, distinct packets. For a few years, this concept was seen by many as just a clever mathematical trick, a temporary fix for a single problem. But it would take the mind of a young Albert Einstein to show that this was not a trick, but a profound truth about the nature of light itself. In 1905, Einstein was focused on another scientific puzzle called the photoelectric effect. It's a simple phenomenon. When you shine a light on a piece of metal, it can knock electrons loose. The classical view of light as a continuous wave made a clear prediction. A brighter, more intense light wave should carry more energy and therefore should be better at knocking electrons free. But experiments showed something completely different. It wasn't the brightness of the light that mattered, but its color, or more precisely, its frequency. A dim violet light could instantly release electrons, while an intensely bright red light, no matter how strong, did nothing. It was as if the electrons were responding to the quality of the light, not its quantity. This is where Einstein made his brilliant leap. he took Planck's idea of quanta seriously. What if, he proposed, light itself isn't a wave at all, but is made of these tiny, individual packets of energy? What if light is a stream of particles? We now call these particles of light photons. Each photon, Einstein explained, carries a specific amount of energy determined by its frequency. A photon of violet light has high energy, while a photon of red light has low energy. This explained the photoelectric effect perfectly. An electron can only be knocked free if it's hit by a single photon carrying enough energy to do the job. It's like trying to knock over a coconut with a ball. If you don't throw the ball hard enough, the coconut won't fall, no matter how many times you gently toss the ball at it. But a single hard throw can do it instantly. In the same way, a single high-energy photon of violet light can free an electron, while a million low-energy photons of red light cannot. This was revolutionary. It meant that light, which for a century had been proven to be a wave, was also, undeniably, a particle. It could behave as both. This strange dual nature was one of the first and most mind-bending principles of the new quantum reality. It wasn't a matter of choosing one or the other. Somehow, light was both a wave and a particle at the same time. This idea was so groundbreaking that it was this work on the photoelectric effect, not his more famous theory of relativity, that earned Albert Einstein the Nobel Prize in Physics. He had taken Planck's key and turned it, opening the door to the quantum world a little wider and revealing that the very fabric of light was far stranger and more wonderful than anyone had ever imagined. The idea that light could be a particle was strange enough, but the next step in our journey is perhaps even more profound. It began not in a laboratory, but in the mind of a young French physicist named Louis de Broglie in 1924. He asked a simple yet revolutionary question. If waves like light can act like particles, could particles like electrons act like waves? At the time, an electron was thought to be a straightforward thing, a tiny, solid speck of matter. The idea that it could have a wave-like nature seemed like a fantasy, but de Broglie proposed that all moving matter, from the smallest electron to the largest planet, has a wave associated with it. This is now known as a matter wave. This wasn't just a philosophical idea. He provided the mathematics for it. He predicted that the wavelength of a particle would be inversely proportional to its momentum. This means that the more massive or the faster a particle is, the shorter its wavelength would be. This explains why we never see this wave-like behavior in our daily lives. The wavelength of a thrown baseball, for instance, is trillions of times smaller than a single atom. It's so unimaginably small that it's completely undetectable. But for a tiny, low-mass particle like an electron, the wavelength is significant enough that it should, in theory, be measurable. For a few years, de Broglie's idea was just a bold hypothesis. But in 1927, two American physicists, Clinton Davison and Lester Germer, confirmed it by accident. They were studying how electrons bounced off a nickel crystal when they noticed a strange pattern. The electrons weren't scattering randomly like tiny bullets. They were creating an interference pattern, exactly like waves would. It was undeniable proof. An electron, a particle of matter, could behave like a wave. This discovery was a cornerstone of quantum mechanics. It meant that wave-particle duality wasn't just a quirk of light, it was a fundamental principle of the entire universe. Everything, every atom in your body, every planet in the solar system, every star in the galaxy, has a wave-like nature. We live in a universe where the distinction between a solid particle and an ethereal wave is not as clear as it seems. Both are two sides of the same cosmic coin, revealing themselves depending on how we choose to look. With the discovery of matter waves, physics had arrived at a strange and wonderful crossroads. The old rules of a predictable, clockwork universe were broken. But a new, unified theory had not yet been built. What was needed was a new kind of mathematics, a language that could describe this world of duality and uncertainty. In the mid-1920s, two brilliant minds, working independently, provided the answer. They were the Austrian physicist Erwin Schrödinger and the German physicist Werner Heisenberg. Erwin Schrödinger focused on the wave-like nature of particles. He developed a famous equation, now known as the Schrödinger equation, which describes how the matter wave of a particle, like an electron, behaves over time. This description is called the wave function. But this was not a wave in the traditional sense, like a ripple in a pond. The wave function Schrödinger discovered was a wave of probability. It doesn't tell you where an electron is. Instead, it tells you all the places the electron could be and the likelihood of finding it at any one of those locations if you were to look. Imagine a single drop of ink falling into a glass of water. It spreads out, creating a diffuse cloud. Before it has settled, you cannot say the ink is at one single point. It is spread throughout the water. The wave function is like that cloud of potential. It describes the spread out nature of a particle before it is observed. At the same time, Werner Heisenberg took a different approach. He felt it was pointless to think about things we could never see, like the specific path of an electron. He believed physics should only be concerned with what we can actually measure, like the light emitted from an atom. He developed a powerful mathematical system called matrix mechanics to predict the outcomes of these measurements. Though their methods looked completely different, they soon discovered something remarkable. They had arrived at the exact same destination. Schrödinger's wave function and Heisenberg's matrices were two different ways of describing the same quantum reality. Together, they created the mathematical foundation of modern quantum mechanics. It was a new set of rules for the universe, and its central message was a profound departure from everything that came before. In the quantum world, you cannot ask, "Where is the particle?" You can only ask, "Where am I likely to find it?" Certainty was replaced by probability, and a new, fuzzier, and far more mysterious picture of the universe began to emerge. Deep within the mathematical heart of quantum mechanics lies a principle that fundamentally changed our understanding of what we can ever hope to know about the universe. It is perhaps the most famous and most misunderstood idea in all of modern physics. This is the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, its core idea is surprisingly simple. It states that there is a fundamental limit to the precision with which we can know certain pairs of properties of a particle at the same time. The most common example is a particle's position and its momentum, which is its mass times its velocity. In our everyday world, these things seem easy to know. A car has a specific location and it's moving at a specific speed. But in the quantum realm, this certainty dissolves. Heisenberg's principle states that the more precisely you measure a particle's position, the less precisely you can know its momentum. And conversely, the more precisely you measure its momentum, the less precisely you can know its position. It's a cosmic trade-off, and there is no way around it. It's tempting to think of this as a limitation of our tools, as if we are just clumsy giants trying to measure a delicate system. To measure a tiny electron's position, for instance, we have to interact with it, perhaps by bouncing a particle of light, a photon, off it. But that very act of measurement, the photon hitting the electron, would inevitably change the electron's momentum in an unpredictable way. While this analogy is helpful, the true source of the uncertainty is even deeper. It isn't a flaw in our measurement. It is a fundamental property of nature itself. It is a direct consequence of the wave-particle duality we spoke of earlier. A wave, by its very nature, does not have a single precise location. It is spread out. To have a definite momentum, a particle's wave function must be a pure, even wave stretching out through space. But such a wave has no specific position. To pin down its position, you have to combine many different waves, creating a wave packet. But in doing so, you've introduced a range of different momenta. This principle is what destroys the old dream of a perfectly predictable, clockwork universe. In classical physics, if you knew the exact position and momentum of every particle, you could, in theory, predict the entire future of the universe. But the uncertainty principle tells us that you can never know those starting conditions with perfect accuracy. The universe, at its most fundamental level, has a built-in fuzziness, a gentle, inescapable uncertainty that is woven into the fabric of reality itself. Now that we have accepted a universe built on waves of probability and inherent uncertainty, we can approach one of the most mind-bending ideas in all of science. It is a principle that completely breaks from our everyday experience, where things are either one way or another, but never both. This is the principle of quantum superposition. In its simplest terms, superposition means that a quantum system, like an electron or an atom, can exist in a combination of all its possible states at the same time. It is not that we simply don't know which state it's in. The particle is truly in all possible states at once, a blurry mixture of every potential outcome. Think of a spinning coin. While it is spinning in the air, it is neither heads nor tails. It is a blend of both possibilities. Only when it lands on the table, when we make a measurement, does it settle into one definite state. Superposition is the quantum version of that spinning coin. Before we look, a particle exists in a cloud of potential. This idea comes directly from the wave function we spoke of earlier. The wave function is a mathematical sum of all the possibilities. An electron, for instance, isn't in a single location. Its wave function is a superposition of all the places it could be. Perhaps the most famous illustration of this idea is a thought experiment known as Schrödinger's cat. It was proposed by Erwin Schrödinger to show just how strange it would be if the rules of the quantum world were applied to our own. In the experiment, a cat is placed in a sealed box with a radioactive atom. If the atom decays, a random quantum event, it triggers a mechanism that releases poison. According to the principle of superposition, until we open the box and observe the atom, it is in a mixed state of both decayed and not decayed. And because the cat's fate is directly linked to the atom, the cat is therefore also in a superposition state of being both alive and dead at the same time. It's important to remember, this was only a thought experiment designed to highlight the puzzle of where the quantum world ends and our classical world begins. But at the level of individual particles, superposition is not a puzzle, it is an observed fact. It is this ability to exist in many states at once that allows a particle to act like a wave and pass through two slits simultaneously. This principle, as strange as it sounds, is not just a curiosity, it is the bedrock upon which future technologies, like quantum computing, are being built. It reveals a universe where reality, at its most fundamental level, remains a shimmering blend of possibilities until the moment it is observed. We now arrive at what Albert Einstein famously called spooky action at a distance. It is a phenomenon so strange, so contrary to our everyday intuition, that it seems like it should be impossible. And yet, it has been proven to be a fundamental truth of our universe. This is the principle of quantum entanglement. In simple terms, entanglement is a special kind of connection that can form between two or more quantum particles. Once entangled, these particles are no longer independent entities. They are described by a single shared wave function, acting as one unified system, even if they are separated by billions of light years. Because of this shared state, if you measure a property of one entangled particle, you instantly know the corresponding property of its partner. Imagine you have a pair of magical coins. You know that if one lands on heads, the other must land on tails. You give one coin to a friend who travels to the other side of the world. You flip your coin and it lands on heads. At that exact moment, you know, with absolute certainty, that your friend's coin has landed on tails. Entanglement is the quantum version of this, but with a crucial difference. Before the measurement, the coins aren't secretly already heads or tails. They are in a superposition, a spinning blur of both possibilities. It is only the act of measuring one that causes both to instantly settle into their definite correlated states. This is the spooky part that troubled Einstein. How could measuring a particle here instantly affect another one across the universe? It seemed to violate the rule that nothing can travel faster than the speed of light. However, decades of experiments have confirmed that entanglement is real, but it's important to know that it does not allow for faster-than-light communication. No information is being sent between the particles. The connection is a correlation that is built into their shared state from the moment they became entangled. The measurement simply reveals a pre-existing, albeit probabilistic, relationship. This bizarre and unbreakable link is not just a scientific curiosity. It is a vital resource that scientists are now using to develop the next generation of technology. From unhackable communication networks to powerful quantum computers. It shows us that the universe is connected in ways that are far deeper and more mysterious than we ever could have imagined. In our everyday world, we are passive observers. Looking at a tree does not change the tree. Measuring the speed of a rolling ball does not alter its path. We assume that reality exists independently of us, and our observations simply reveal what is already there. The next step in our quantum journey challenges this fundamental assumption. This is the concept often called the observer effect. In the quantum realm, the act of measurement is not a passive process. It is an active and transformative event. Observing a quantum system fundamentally changes the state of that system. This idea ties directly back to the wave function and superposition. As we've discussed, before a measurement is made, a particle like an electron exists in a superposition, a fuzzy cloud of all its possible states. The wave function describes this cloud of probability, but the moment an observation occurs, this cloud of potential instantly collapses into a single, definite reality. The particle appears in one specific place, or with one specific spin. The most famous demonstration of this is the double slit experiment. As we know, if we send electrons through two slits without watching which slit they go through, they create an interference pattern. They act like waves. This happens because each electron is in a superposition of having passed through both slits at once. But if we place a detector at the slits to observe which path each electron takes, the very act of observation changes the outcome completely. The interference pattern vanishes. The electrons stop behaving like waves and start acting like simple particles, forming two distinct bands on the screen behind the slits. The knowledge of the electron's path forces it to choose a single state, destroying the superposition that allowed it to be a wave. Now, it is crucial to understand that the observer in quantum physics does not have to be a conscious human. It can be any interaction with a measuring device or the surrounding environment that extracts information from the system. The universe, it seems, does not like to hold on to its quantum secrets. Any interaction that reveals a particle's definite state is enough to collapse its wave of possibilities. This principle forces us to reconsider the nature of reality itself. Does a tree falling in a forest make a sound if no one is there to hear it? Quantum mechanics takes this riddle to a deeper level. It asks, does a particle even have a definite position if nothing is there to measure it? The answer, it seems, is no. In the quantum world, reality is not a fixed stage that we simply watch. It is a participatory event that we influence with every observation we make. It is easy to think of the quantum realm as something distant and separate, a strange world that only exists in laboratories or complex equations. But the truth is, the principles we've been exploring are not confined to theory. They are the bedrock of our modern world, the invisible engine running inside the technology we use every single day. Every time you use a computer, a smartphone, or even a simple television remote, you are using a device built upon the laws of quantum mechanics. The heart of all modern electronics is the transistor, a tiny switch that controls the flow of electricity. A single computer chip contains billions of them. And a transistor only works because of the quantum behavior of electrons moving through semiconductor materials like silicon. Our entire digital age is built on our ability to understand and control these quantum effects. The same is true for lasers. The pure, focused beam of light from a laser in a barcode scanner or a Blu-ray player is a direct product of quantum physics. It is created by electrons in atoms jumping between specific, quantized energy levels and releasing photons in a perfectly coherent way. Even the ability to navigate our world with GPS relies on quantum precision. The satellites that guide us use atomic clocks, the most accurate timekeeping devices ever created. These clocks work by measuring the incredibly consistent frequency of atoms as they transition between energy states, a purely quantum phenomenon. Without them, GPS would be hopelessly inaccurate. The very light and warmth we receive from the sun is also a gift of the quantum world. As we'll explore later, the process of nuclear fusion in the sun's core, where hydrogen atoms join to form helium, is only possible because of a quantum effect called tunneling. The strange, probabilistic, and uncertain world of the quantum is not a separate reality. It is the fundamental operating system of our universe. The technologies we often take for granted are a constant, quiet reminder that this hidden world is not just real, but essential. As our exploration comes to a gentle close, let your mind drift over the ideas we've shared. We have journeyed into a world that is fundamentally uncertain, a world built not on solid facts, but on shimmering waves of probability. A world where particles can be in many places at once, and where strange connections can span a universe. It is easy to think of this world as separate from our own, but it is not. It is the world beneath the world. The same quantum rules that govern a distant star also govern the very atoms that make you. Every part of you, every breath you take, every dream you have, is unfolding according to these strange, gentle, and uncertain laws. There is a deep peace in this thought. Our waking world often feels so rigid, so defined by hard lines and definite outcomes. But the universe, at its core, is softer. It is a place of potential, of possibilities waiting to be realized. So as you settle deeper into rest, you can let go of the need for certainty. You can allow your mind to embrace the gentle fuzziness of reality. The universe is not a clockwork machine, but a quiet, unfolding story, and you are a part of it. Thank you for joining this journey into quantum physics. I hope you learned something new, or at least found a moment of peace. If sleep hasn't found you yet, feel free to explore another calming video on the channel. Until next time, stay curious and have sweet dreams among the stars.